So, welcome. 20 years ago, I was lucky enough to get my first car. And I'm not sure what your first car was, or if you ever own a car, but for myself, it was freedom, right? Finally, I was able to drive around and impress with my technology on the car. Unfortunately, back then, I was also a bit underwhelmed about the, let's say, technological masterpiece of presenting navigation and your car data, like your speed and so on, right? Nowadays, that's second nature. You have those huge displays and you have your navigation built in, but back then it was more, let's say, appliance-based with the TomTom on top of your dash, right? So I tried to improve that. And I was studying software engineering back then, and I thought, maybe I can change the centerpiece, like building my own displays and my own HMI and my own board computer to impress, right? So let's start. What can I use? Tablets back then wasn't really a deal or really existing in a way I can use. So I used the next best thing and used an ePC. Who used that before? 5 people in this room. That was more or less the pinnacle of mobile computing. You have this super small laptop with a little display, was super cheap. So I have gone to the next shop, bought one, tore it down, right? Disassembled all the pieces, and I thought, maybe I can just flash Android to it. Maybe I can put on a touch display or a touch overlay, and maybe I can connect the GPS and onboard information with this computer. And after some prototyping, that was the pinnacle of my prototype. You see, professionally made from duct tape with some styrofoam, and along with some pretty heavy-duty glue that disassembled itself every third time, I was able to build the first, for myself, my first board computer for my cool little car. And I was able to drive around until this. There was a bit of a usability problem back then, because now I was able to touch it, but I was like, not really sure where the buttons are while you're driving, right? So totally normal. But unfortunately, my car, that was really my car, got hit by a lorry and got compacted, so I needed to move and migrate to a new car, and I dug more into how cars actually worked, because the next iteration was not only about the display. This time, I want to integrate it with the onboard network. And this is really astonishing how the actual network inside a car works. Have you ever tapped into a car network? Then you see it's more or less computers, small little pieces that are interconnected with this small little CAN bus, if you ever heard about that, right? So it's more or less drilled down wires and all the things like your onboard computer and your touch display, they are more or less along with more things connected to that. And so you drive around your little network of networks, which is quite a complex system, in every car. And more or less 100 to 160 of those little computers are in your car, and you're driving with that every day. So how can you tap into that? So The car network, of course, is not only for engineers, it's also for car theft, right? Interesting. So what you want as a car thief, as you have seen this here on the front, they are working with the headlights. And if you go back to the car network, you see, okay, some of those wire harnesses, right? Those blue ones and purple ones and Turkish ones, turquoise ones, those are moved around the car, and some also end up at places you won't expect. And car thieves use that to their advantage to steal your car. So they, for example, take out your headlight, tap into the network, and tell your doors to open. So again, from a topology perspective, this is more or less a bus that's spread out into stars, and you just need to figure out where each of the components are. So I, for myself, tried to figure out where is the information collected on the engine, and tried to get, for example, the speed and the RPM, the rotations per minute, and displayed on my little device, right? So this also can work, but nowadays, if you go into the car domain, you will be seeing a lot of topology attacks because security in those networks is not that good, mostly because of safety. And this is also what the prototype of each and every car hack is, right? If you work with this, this is more or less obvious to you that, of course, if you have a car network like this and you gain access to it, you can do shenanigans with that. And two hackers 10 years ago showed this in this famous cheap hack quite interestingly, because they showed how to get into your car over the cellular network, move around the internal network of the car, and then tap into the driving functions like go left and right, and drove a car into the trenches as a prototype attack. So security in those vehicles can be considered safety relevant, right? So if you're working from a network perspective, if you have access to those networks, that's a safety concern, and we need, if we're in that space, keep an eye on that. And not only from an individual vehicle perspective, you can imagine huge fleets of vehicles are moving around and connecting to services, which are again mostly in the cloud, at least with the people I'm working with. And if you have those cloud services and they're compromised, of course, this could be a way into your cars and end up being a hazard for hundreds and millions of people. So let's dig into one of those hacks in more detail. This famous cheap hack, for example, they moved from the cellular network on the left into one of the head units, and from one CPU to another, and then jumped into this driving functions. Again, this is all network-based, right? So as you're inside the car, you can talk to the network and tell the parts inside your car what to do. Again, this led to a recall of 1.4 million cars, so it's relevant for us. But why is it relevant to you? In my opinion, nowadays, this vehicle world and this automotive world is moving quite fast and is pressured by regulation heavily. So now, in the last years, we have seen a shift from being in a security state of, okay, the cars are more individual, to a consideration of, okay, we have huge fleets and they can all be attacked. And they're pressured by regulation, so they need to show that a car is cyber secure, and otherwise they can't really sell it on the EU market and also in other parts of the world. And this is also considered updating your software inside the car. So everything is software, right? And you need to find out, okay, how to do that. And so also the topologies of the cars changed, like the IT world, from a very central bare metal dedicated part of the game to a more distributed way, and then to a more modular way to say, okay, that's all software, and we want just to run parts of software on our vehicle platforms. And nowadays, we see this shift again in the cars, that from this bare metal approach to more, okay, we want to virtualize it, to more, okay, we have a common kernel, and we want to containerize, because if we put an expensive ARM platform in our car, of course, we need to update it. So we see this shift heavily, and therefore, the Kubernetes and cloud-native world is very interesting also in this space. The big players took it up and picked up the ball and built, again, platforms for that. So we're seeing nowadays virtualization and container platforms in this space. For example, to show you the HMI, so like the human-machine interface, your visualizations, as well, of course, as putting data or getting data from the car and putting it on cloud storages for further processing, like your camera data in an anonymous way. You see this also inside the cars. This is from Black Hat, for example, some years ago. There are those platforms, those ARM platforms that are running more or less virtual machines and containers. And this talk was about, okay, how is it distributed inside the network? So much for the primer. This talk is about eBPF in cars. So how can we do it? Again, if you have a platform like this, an ARM platform, for example, and it's running your software as containers, so you have a container image, maybe you pull it from somewhere or just store it on the machine and run processes side by side, how can you, if you think back to this attack where the thief pulls into your headlights, how can we defend an application from the attacker using eBPF? That's the main question of this talk. And the answer is, if we look at the attack path, this network part is a big, so to say, jump into your systems. So let's consider this more thoroughly. So in the lab, you can prototype this. So for example, sorry for the sound. If we're in the lab, you can pull out some of the components and figure out how to communicate. Again, it's just a network, so they're sending frames of information, and the hardware is interpreting it and displaying you something. This could be a very physical thing like this. This could also be like your panorama view on your newest super cool vehicle. But in the end, it's just data. And this data is, if you take a scope, just on the wires. This data gets consumed, of course, by a transceiver, like a network card, right? And then presented to the kernel. Same, like Ethernet. So we just need to figure out how can we use eBPF on this network. And the answer is same. You just write programs, compile it, and load it into the kernel. And then you attach it on the right spot. Who wrote or who used eBPF before? 7.5. And who wrote eBPF before? Cool. We need to talk. And if you never did this, it's quite easy, right? You write the program, it's C-like, everybody can read this, right? It's just, okay, there's a specific point where this eBPF program gets called, and then you get a context. It's just data or a pointer to data. You need to interpret this data. In our case, we look at an executed program, and we could recover the program name. And this is eBPF, right? And this is compiled to this bytecode, and that's loaded into the kernel. How can we do it on the network? We take one of the network-related attachment points. So if you used it in your Kubernetes cluster, I don't know, you use Falco or Tetragon or Cilium or your Envoy proxy, that's the same thing. It taps into your network and calls a program as it receives a network packet, right? So here, again, you take one of the network-related calling attachment points, and you say, okay, you have an application that's containerized. You present the CAN bus. It's just like an Ethernet network, right? You present the CAN bus inside the container, and every time that this interface is receiving a network packet, then your program gets executed. Quite easy, right? So you write this. You just write the code that takes the packet, buffer, decodes it, blah, blah, blah. So that's a bit of shenanigans. And in the end, you can process every frame, every CAN frame, like a network Ethernet frame, from the network and do something. And in the back, you have more or less on the right here, the electronics side of things, which is completely on its own, like in the Ethernet network as well. They also do electronic stuff, right? But we are not concerned. The only thing you need additionally is, of course, something that manages it. So you need something that takes your eBPF program and loads it into the kernel and attaches it to the correct network interface. Boom, boom. You can more or less nowadays Claude code it or ChatGPT it in 20 minutes if you're faster than me, but I'm very slow, so I need 20 minutes at least. And then you have a little program that loads the actual eBPF program. And in the end, you just need to decide, okay, where I want to connect it to, right? Or where do I want to attach it? And this is more, if you're into networking, that's of course cool. If you're not into networking, you just need to know, it depends which layer you're interested in. Is it at the point where the socket opens? Is it at the point where it's like queued into the Linux networking? Is it at the point it actually gets out of the network card? So at the latest step or at the first step as you receive network information. So this decision is more engineering. You decide here. I decide in this case, I do it at the first step from below. So as you receive a network frame, then I jump in. And indeed, then this CAN data, so this is an actual traffic captured. So you see on the left, there are some IDs involved and data, but this is how CAN looks. It has no source, it had no destination, it's just ID and data. So it's not very, very hard. Let's break my next car. And this is always where my wife is not very happy when I take my laptop with some electronics and go to my car and say, please don't wait, it will be late, I'm in the car. And the next day, it doesn't work again. So, words of warning, if you ever work on your own car, try to figure out how your kids get to kindergarten the next day. Otherwise, you'll be in big trouble. So if you don't have this problem, take your laptop, go into your car, you can tap into the network at the correct point, I can show you where, and then with sometimes some disassembling of mine, sometimes it's quite hard to get into that, then you have on the left a little board computer like me that's always connected to the outside world and sometimes drains my battery and then I can't start my car anymore. But you have then a thing that's on your system, and the companies I'm working with, of course I don't do that, but here we try to work how to protect, for example, your board computer from attacks, right? So how does it actually work in the end? And thank you for your patience. On the right, you have something like TCP dump for the car network, so you see all the data. And on the left, you see, as you, for example, load the eBPF program, then something happens. And if you, in the middle, attack your car or try to fiddle around with your electronics, then this program inside the kernel triggers and shows you, whoops, there's something going on. And if you're into car mechanics, you would immediately recognize the bytes on the left, which maybe somebody already sees it, is diagnostic information. And of course, you can come up with more cool things like, of course, what about more elaborate filters? And there we actually now arriving at the stage where we can say, maybe I know an attack and it's out there in the wild. And I want to create a program that's lightweight, sitting in the kernel, and protect my unchanged application as it runs. And with eBPF, I can do that to a specific point. Here we actually loaded a program and it changes nothing. And at a specific point, we change how it works. And here only specific informations that are checked are delivered through to the actual container to your application, and the others are blocked. And here you can create more elaborate defenses because you have the full control of the data buffer you're working with. So this is another example which I won't go into more detail. I also did this with onboard communication. For example, if you have an update system and it flashes your actual computing unit, then I would like to control that as well. Otherwise, an attacker could just flash your system, which I also sometimes do during penetration testing. And in conclusion, of course, it depends how the actual car is built. So if you have the luxury as a manufacturer, for example, to have an onboard computer, you can, of course, deploy quite complex software there. But then, of course, the question is how to come up with even complex defenses. Because the attackers locally just needs one or two hardware adapters to tap into your car and start fiddling around with it. And as they do, they may stumble upon important information. And of course, it comes only down to what information is transmitted. And maybe we can, with eBPF and cloud-native technologies, come up with defenses here. And this is my takeaway from today for you, in my opinion. We need to step up our game and be a more software-defined defense approach, or to have one of those, rather than having it all in hardware and final no changes at all, right? We need to step up our game and come up with more flexible defenses, because every program could be your downfall. And with that, I hope I won't break my car again, and thank you for your attention. If you have any questions, I think we have one more minute to take them. If not, you can also check out the repository with the actual code. There's a question. Yes. How to protect your car against. So how can we defend in our cars with the example of row hammer attacks? That's a very good question, and we see in the car networks there are like gateways and firewalls already in place. I think there are, or as far as I saw in real life, there are also some protections on the actual electronic control units, so the things that operate your car. But from a more software-defined SOC approach, we're sometimes a bit far off compared to the IT, let's say. There are SOCs for cars and vehicle fleets in place, they work, but not in a way like we're used to it in IT. Can I have my display again for a second? Thank you. If you ever want to play with this, with CAN hacking as well, just ping me at my LinkedIn and I send you a link to a not yet published, the later free course on car hacking with also eBPF. So that's all in the browser. You don't need to do anything, but you can also read up all the information I just gave you. So how to write the programs, how to load that, and how to actually prevent something from happening in your browser. Everything is prepared. So just maybe send me a LinkedIn message, please course, and I send it to you. I'm happy to have your feedback on that. All right, thank you.